going on, man? Get the gun.
It's over, Carter.
You okay?
Yeah. I'm great.
We got him, man. We got him. Let's get out of here.
Hollywood movies always have some element of inaccuracy. After all, the scenes shown are not necessarily meant to be realistic. They are oftentimes sensationalized for the sheer amusement of the audience viewing the movie. However, sometimes these movies stretch it too far. When it comes to scientifically inaccurate scenes, this scene from Too Fast, Too Furious, that of a car flying onto a boat after gathering enough speed and getting boosted off a ramp, takes the cake. Here's why. First of all, let's define the variables in this scene. The mass of each passenger is estimated to be 75 kilograms. We further estimate the speed of the car to be 53.6 meters per second, and assume that it projects from the ramp at an angle of 30 degrees above the horizontal. In the scene, the car only clears approximately 7 car lengths, about 33.4 meters, and the period of flight lasts for about 9 seconds. With the above estimated variables, we can now use some calculations to prove the sheer improbability of the scene. Of course, for calculations to be made, we assume negligible air resistance. Horizontal component of velocity is a constant, and can be found by v equals to 53.6 cosine 30, which equals to 46.4 meters per second. Considering vertical motion, v equals to 53.6 sine 30, which also equals to 26.8 meters per second. Assuming the eventual vertical displacement of the car is 0, we use the kinematics equation s equals to ut plus half at squared. Since we know displacement, initial velocity, and acceleration, we finally deduce the time of flight to be about 5.46 seconds. Hence, time of flight of the car is about half of what is seen in the movie. Furthermore, considering the horizontal displacement of the car, s equals to ut, which also equals to 46.4 times 5.46, which also gives us 253 meters, we are able to deduce that the car would have flown way too far to possibly land on the boat. The car would have overflown the boat. Of course, let's then assume for a second that the car actually hit the boat, since in real life there is air resistance and the incline of the slope could be less. However, it is still impossible for the protagonist to have come out with seemingly no bruises and unscathed. By the impulse momentum theorem, the impulse of the net force acting on a body in a time interval is equal to the body's change in momentum during that time interval. Hence, F net equals to dp over dt. Therefore, average force equals to momentum times time. Since the final momenta of the passengers are 0, the change in momentum of each person would simply be the product of their mass and velocity, P equals to mv, which also equals to 75 times 53.6, or 4020 Newton seconds. To find the average force exerted on the bodies of the passengers, let's assume that the time of collision lasts for about 0.5 seconds. F net equals to 4020 over 0.5, which equals to 8040 newtons. To find the effect of the collision, we will need to calculate the g-forces that each passenger experiences using the formula F net equals to ma, or 8040 equals to 75a. Hence, acceleration is 107.2 meters per second squared, which equals to 107.2 divided by 9.81 g's. This amounts to about 11 g's of forces. The average human can withstand only approximately 5 Gs of force over a small time frame before passing out, with 11 Gs of force experienced due to the rapid deceleration of the car. The old corner should not have been in good shape that we saw him, toting a gun after a collision that could have been fatal due to internal trauma sustained by human organs.